is good. Do you see it?
There you go.
Yeah, all right. You never know with Linux, right? Cool. So, how's it going, everyone? Like you said, my name is Eddie Zaneski. I'm a software engineer at a company called ChainGuard, where we do open source software supply chain security. I'm actually a maintainer of the Kubernetes project. That's what I spend most of my time working on. And you can find me everywhere on the internet at Eddie Zane. So Twitters, GitHubs, emails, all those things. And we're going to talk about how cryptography isn't scary, it's fun. Except I have to give you a really scary disclaimer to start. I am not a cryptographer. We'll get into more about why I'm giving this talk in a second, but everything I'm showing you here today, take as an educative purpose. Don't copy paste this and pipe it to production. Anytime you're doing authentication, anything with crypto, don't roll your own, right? Use a service, talk to a professional, work with a cryptographer. So again, don't try this at home, except if you're gonna have fun and stuff. So cool, everyone promise? I made my cryptographer a deal. Okay, cool. So why give this talk, right? So I'm not a cryptographer, and I just joined this company that I'm working for back in March, knowing nothing about security. And so how do you go from working on distributed systems and containers for years to working at a computer security startup without knowing anything about security? And so I went on this big research sprint and just tried to learn and teach myself as much as I could. And that's something I love doing, is just learning new things. And so as I was learning more about cryptography, in the back of my head, I'm always thinking like, oh, like you have to have a PhD in math to be able to do this, or it's not for the pleb. I should never touch anything to do with a hash or encryption function. And that just turns out to not be the case. Again, consult a real cryptographer. But it's the idea behind cryptography is actually super fun. And there's a lot of cool primitives and higher level ordered things that those smart cryptographers have built that we can play with. So quick rundown on what we're going to talk about today. We're going to go through some terms, talk about keys, talk about this awesome thing called Diffie-Hellman key exchange. We'll look at how crypto works in JavaScript in the browser and Node. We'll talk about this potential really cool story of the NSA backdoor. It's my favorite story that I come across while learning. And then we'll talk about some cool stuff going on with NPM and this other project I work on called SigStore. So if you talk to a modern cryptographer, they're going to tell you, we have a handful of things that really make up modern cryptography. And so we have this idea of symmetric keys, right? So a symmetric key is a key that we agree on ahead of time, and it's shared for encryption and decryption, right? So we agree on this key, and it's just the one key to rule them all when it comes to a cipher or any kind of text. And that's cool, but it doesn't always work because that's a single key that can get leaked. If everyone has a copy of this key, it's pretty dangerous. There's pros and cons to do it. So we also like to do what we call asymmetric cryptography, or private key, public key crypto. If anyone's ever used RSA before, or SSH, you've used public key crypto before. And so this is an idea that you can derive some private key, so depending on the key type, so you come up with some secret, and from that secret you can derive a public key. And so that public key can always be tied back to your private key. So if you sign something or encrypt it with your public key, only the person who owns that private key can decrypt it or verify it. We also talk a lot about one-way functions. These are mathematical functions that are easy to go forward with, but really hard to reverse. A lot of this comes down towards prime factorization. So you take two really big prime numbers. A prime number is a number that can only be divided by one in itself, and you multiply them together, and so you have this huge number, and then to go and reverse those two numbers out of that huge number is really hard. It's a discrete logarithm problem. So we rely really heavily on these one-way functions. And also pseudo-random number generators, right? So computers, they're sand that we've tricked into thinking, right? They can't actually be random. They only do what they're told. And so when it comes to randomness in your computer and your software that you're writing, it has to use some source of randomness, some source of entropy, as we'll call it. The modern Linux and Unix kernels will have a pool that gets picked up from every mouse movement, every keyboard press you type, every packet that gets sent over the network. It pools all of that randomness into a source that can be pulled from for cryptography. And so these last two are really important because modern cryptography stands on the shoulders of these two, right? If those one-way door functions become realized, like, oh, there is a secret shortcut to undo it, like the world will end, right? Like it will be completely terrible. Same thing with pseudo-random number generators. If for some reason you're able to reverse this random number generator and predict the next number out of it, like you've broken all of cryptography today. So RSA is, this is the reaction you'd get if you talk to Zach, who's the cryptographer that I work with, when you talk about RSA. It was great when it was invented back in 1970-something. It has since then been replaced, basically, right? So the way that RSA worked was with that prime factorization with a lot of modular arithmetic, which I'll show you in a second. And so RSA was great when it came out, but it's time for something new, and new things exist that are proven stable. So that's what we're going to talk about for RSA. So modular arithmetic. Anyone remember doing this in school, math class? Maybe a little bit. Anyone ever used a percent operator in JavaScript? Yeah, you've done modular arithmetic. Hey! So this is the idea that we take a number, and instead of doing division and figuring out how many times a number goes into something, all we care about is the remainder. And so if you see here, if we take 13 mod 12, we get 1. So 12 goes into 13 one time, and there's 1 left over. 14 mod 12, there's 2 left over. Makes sense. 28,000, big number, mod 12, there's also 2 left over. Right? So if I give you a key or some sort of secret that says, hey, like whatever my secret is, mod 12 is 2, you have no idea if you started with 14 or if you started with a massive number. Right, so this is also one of those one-way door functions that's really hard to reverse. And so we use modular arithmetic in all sorts of cryptography. You just sprinkle in a little mod math when you want it. And so what's recommended today is this thing called elliptic curve cryptography, or ECC. So I came across this felt pretty fitting. I'll give you a second to read it. I thought this was funny when I was Googling it. Right, so elliptic curve looks like the picture on my right there. It's sort of a bell curve, right? It's in 2 dimensions. And so when we work with elliptic curves, these are not just someone your teacher gave you a random math problem to solve. This is a really researched piece of cryptography, a really researched mathematical formula. The basis of all of them is this y squared equals x cubed plus ax plus b. You never have to remember that ever again. Does anyone know what this curve is used for? Anyone recognize that? Bitcoin, I knew someone would. So this is the curve that is used for all of Bitcoin, all of the public blockchain. So all keys are derived from this single curve, right? And you can see here that these are the parameters that define this curve. So this is probably the most well-known curve in the world. It's recognized by most of the government agencies just because of its usage in crypto. And so what I found really interesting was learning about this is how these keys are generated, right? We're no longer generating like really big prime numbers. We start off with a curve, right? So we agree on a curve. That curve has a public point called P. You can see that in here. It's also sometimes called G. It's that point right there, the third from the bottom. And so we agree on this P/G point. And then we come up with another random point. So sometimes you'll draw a tangent line and figure out where it intersects, or you can pick one at random. And so let's say we wind up with this Q. This process called the dot function, that's what it's referred to in the formulas, is we draw a line from our generator point to our random point, and it will hit the graph at most 1 more time, right? And so if it does, we call that R, or negative R in this case, and then we do a reflection down to the x-axis, and we come up with the real R, right? Or you can call this 2P or 2G, right? And so we just keep doing this over and over again. And so now we have 3P, right? And so you can imagine that as we wind up with a point on the graph, and I say, hey, what number P was that? Well, that's actually really hard to figure out, right? And so that is actually what our private key is. And so the solution for public-private key for elliptic curve is the coordinates of this point is our public key, but how many times we did the dot addition function is our private key, right? And so you imagine just at a huge massive scale, this is another discrete logarithm problem. It's very hard to solve. So I thought this was super cool and very simple as a sounding point for giving a key. All right, and here's a quick animation of how that looks. You just do this over and over again until you wind up with a huge enough point. Well, the reason that we use ECC instead of RSA is that computers have gotten smaller and they're everywhere, right? From factory equipment to a super genius device in your pocket. The problem with RSA was to get stronger with RSA, we had to keep increasing the bit length as computers that could brute force and break these keys are hard, right? And that's why this one-way door function is so important, because it is only possible right now to brute force a solution, right? There's no shortcut. And so you can see as RSA key length has grown, you can get the same amount of security bits for a much smaller key for ECC. So this is one of the main reasons that people recommend ECC. And so that leads us to the Diffie-Hellman key exchange. Has anyone heard of this before? You use it every single day, multiple times a day. Anytime you make a web request in your browser or your phone, this is how a TLS connection or SSL connection is established between your client and the server. And so it's a way that we can agree on a symmetric key over an insecure channel, and it allows for future symmetric key encryption. So this is a very simplification of it, right? And the way this is explained usually is with colors. So let's say that we have Alice and Bob who want to communicate, and there's Eve, who is a nefarious third party who's always listening. And so we obviously have to communicate in the open to start. And so we agree on a public color, right, or that public point on that graph. So everyone knows this color, even Eve. And then Bob and I will pick a secret color, right? So we each picked a secret color. If anyone's colorblind, I tried to put the words on there, so I'm sorry. And so then we take that public color and our secret color, and we combine them, right? So we get orange and green. We swap those, right? At that point, it is a public piece of data. Eve winds up with orange and green. But the neat part is that we also have our private key, so I can mix in my red from that green that Bob gave me, and I get brown. Bob can do the same thing on his end with the orange I gave him, and he also gets brown. Eve can't get brown, right? Eve has no idea what that secret color is. And so this is basically the same thing extracted on that elliptic curve. And so I'm going to show you real quick, just a reminder to open the console, that if you ever look inside of your tab, in the security tab, you'll see here, under this connection bit, this says, this connection to the site is valid and trusted using QUIC, which is a protocol, X25519, which is a curve name. It's the Diffie-Hellman key exchange curve name. The X is for the exchange. And then we have this AES 128 symmetric key encryption, right? So that's pretty much what we did in here. And so an example of what this looks like in Node's crypto library. So quick disclaimer on Node's crypto library. It is very old, right? Node as a piece of software is pretty old. And it's built around OpenSSL, which you've seen updated when you brew update many times, and maybe it breaks everything. But Node relies heavily on OpenSSL, and it has grown as an API surface. So you'll find many functions that are called the same thing, but take different parameters as they realize how to actually do this. So this is what this looks like in Node, right? So we import crypto, we generate that key pair using that curve name. Alice and Bob both get public and private keys that we can pass into this Diffie-Hellman, right? We can swap my public key and Bob's private key. And then at the end of that, we get that secret that we agreed on, right? So this is our AES symmetric key encryption. So we have this shared key, so now what do we do? And again, this is what your browser is doing in a very, very high-level summary version, right? So we have a secret. I can take that key. I only need 16 bits of it, so we either agree to take the first or the last 16 bits. Then we have to generate this initialization vector, which is just kind of random data. The thing with hashing functions like SHA-256 is the input is always going to be the same for the output, right? So if you always put in a file with the same contents, the output will always be the same. That's why we can use hashing functions to verify file integrity. The problem when you're doing cryptography is if you're using the same inputs for the same outputs and you see the same thing coming across the wire, it's pretty easy to guess. So we inject a bit of randomness at the front there. I use my stuff to create a cipher, update that with my secret, usually just stick that IV onto the front of your encrypted text. It's considered public data, and then your client will reverse it, or the browser will reverse it. Cool, makes sense. Quick demo. You can see I generated those keys. You've seen, this is a key in encoding protocol called PEM. And so you've probably seen this before if you've done your SSH keys, uploading to GitHub or a server. Right, so there's our public and private keys. We agreed on that same shared secret at the end of the day. And then we do our crypto ciphertext, and our output is the same. Cool, that works. So that's Node. So what about the browser? Well, the browser's actually come a really long way. The Web Crypto API has 3 high-level top things. There's this get random values bit where you can give it an array of like typed unsigned integer 8, and it will fill it with random numbers. Random UUID will give you a v4 UUID, which is cool. Again, this is baked into your browser. You used to have, if anyone looks on Stack Overflow, you'll find this like crazy regex to generate UUIDs that people used to recommend. Now it's just built in. And then there's the subtle crypto library. It's what's called subtle for a reason, right? Again, back to that disclaimer. It is really easy to shoot yourself in the foot because these functions and these methods have subtleties to them. So when you look at the MDN docs, you'll see big, scary warnings. But these are all the things that are supported in the browser, right? So it might be tiny, but you can sign, verify, and there's the key types that work with it, encrypt, digest. So it's pretty full-featured, and the API is great. So definitely recommend checking that out. Again, this is that subtlety. So if you go to MDN's docs, you'll see some scariness there. But as far as crypto goes, like you can do a ton in the browser. So that leads me to my favorite story, which is this possible NSA backdoor that may have existed. So there was so get back to those pseudo-random number generators. This is what do they call this? A cryptographically secure pseudo-random number generator, so CSP stuff. And so this was a way that the NSA came up with to generate random numbers. And it works based on elliptic curve cryptography. And so you don't have to care too much about this, but what's important for a number generator is it needs to maintain some sort of state internally, right? So it knows what the last number generated was, and it can feed the last number it spit out back into its input to use for more randomness. Well, NSA came up with this, and they showed a bunch of people how it worked, and then I think people were super skeptical from the very start. Within a year, 2 cryptographers from Microsoft basically were like, yo, this is super shady. There's a potential backdoor in here. And so, again, this little flow graph here, right? So S is our state. S times P is that point on the graph. R is the randomness that comes out. And you take that random number, you multiply it by Q, and then you truncate the last 16 bits of it. 16 bits is pretty insignificant, so that was their first red flag, was like, you're not taking enough bits out of this. But if you spend enough time researching and reading this, P and Q this is a decent cryptography pseudo-random number generator in theory, right? Like, if P and Q are truly random. But let's say that P and Q aren't random. Let's say that actually P is influenced by Q, right? So let's say that we came up with Q and another number, E, multiplied that together to get P, right? So in theory, this E might exist. Well, if that E exists, and you do some association property on this, you wind up with that E times RQ equals R times EQ, and then EQ is, as we already said, P, right? So now we have RP. So we basically found the internal state of that pseudo number generator, right? And if you have the internal state, if you can predict the internal state from that output, you can guess the next number. And again, back to the start, cryptography is broken, right? So, okay, cool. It gets better, right? So this is 1,000 times slower than current modern ways that we generate random numbers. Cool, okay. If it's better, better generation, maybe people will use it. It doesn't matter that it's that much slower. Cool. Well, the NSA came up with that P and Q. Okay, cool. Like, before Snowden stuff, we used to trust the NSA to do crypto for the US government. Cool. NSA wouldn't tell people where P and Q came from. They wouldn't tell them how they arrived at those numbers. So it got a little sussier. NSA then paid the RSA company $10 million to make this random number generator the default in the Be Safe security SDK that RSA publishes. So now you have money changing hands. And then on top of it all, NIST is the National Institute for Standards and Technology. So NIST worked with the NSA, and the NSA basically forced NIST's hand to say, you are only FIPS compliant if you use this P and Q out of our numbers. Right, so as you learn more about this, it just becomes shadier and shadier. And modern cryptographers are absolutely convinced that this E exists and that the NSA knows it and that there is a backdoor. When the Snowden docs leaked, it all as well confirmed that this happened. Really, really encourage you to check this out. It's probably the best story that I've heard in a while. Computerphile has a great video on it, as well as this blog post is really good. So I have a link to the slides at the end. And so that brings us to SigStore. Has anyone heard of SigStore yet? No? OK, that's awesome. So SigStore is a new standard for signing, verifying, and protecting software. And so SigStore is a Linux Foundation project, spun out a sub-foundation called the Open Source Security Foundation. And we like to describe this as Let's Encrypt for signing, right? So Let's Encrypt kind of took the web from having, what was it, like 20% SSL certs to we're at like 80 or something now. And so that's the idea behind SigStore, because developers managing signing keys is hard, right? Like, it's hard to keep a key. What do you do when you get a new laptop? Do you copy paste it? Do you put it on a USB drive? Are you sure you wiped it? Did your key expire and you forget to rotate it? We see people all the time forgot to renew their SSL certs or their domains. So just keys in general are really hard for developers to do. And so SigStore has a bunch of different components. The most notable to talk about is this Fulcio component. It's what we call keyless signing. It's this idea that you can tie a public identity, so through OIDC, to a crypto key. And so I can go and I can log in and OAuth to GitHub, get a one-time use signing certificate that's tied to my GitHub account, and that key is only valid for 10 minutes. So it really doesn't matter what happens to it afterwards. And even though it expires, it all goes into this public transparency log that can be verified, that Eddie had access to this signing key because of his GitHub account within this window. There's also some other components in here for container signing and git commit signing. But the best is SigStore.js. And so this was built by Brian DeHammer, who's on the package security team at GitHub. It was donated to the OpenSSF and the SigStore project by GitHub. So big shout out to them. And the cool thing here is this has provider support built in. So inside of every GitHub Actions pipeline is a OIDC token that identifies your, OIDC is like OAuth and OpenID Connect. It's built on top of the OAuth spec. And so in every single GitHub Actions pipeline run, there is a token that identifies the run, your commit SHA of your code, basically everything. And you can take this token and exchange it for things. So this is great because inside of our pipelines, we can exchange this tied to a user, tied to a actions run for a key to sign with. Really cool. So there's support in the works for other providers, and we encourage other CI/CD providers to get involved. And we're always looking for new contributors. The reason I'm bringing all this up is there is an NPM RFC out right now called RFC 626. It is an RFC for linking packages to their source and build. For the sake of time, you can link public NPM packages to the source code repository and build it originated from source, making it harder to execute package hijacking attacks or malicious versions. Right? So this is the idea that someone compromised your NPM credentials, you don't have 2FA, and they published a malicious package on your account. A little different from what happened with LeftPad and some of the other things out there. But this is a very real-world thing. And this actually happened to the Python community last week. I don't know if anyone follows that. But the Python maintainers and PyPI package maintainers were subject to a spear phishing attack. And they had their credentials stolen and a bunch of malicious packages published. So this is the kind of thing that SigStore would prevent. And so real quick, I'll show you. We can npm pack this SigStore package. And then I can sign that. It's going to pop up in my browser that I want to OAuth, so OAuth with Google. It'll do the exchange, give it back a key, and then I got a signature for this package. So I can grab that log index ID, and this is the important part. So I can show you here that this is the cert and the inclusion, and you can see that this was signed by my email address. Really cool project. A lot in the works right now, so check out the NPM RFC. Before I get thrown off the stage, if you want the copy to these slides, you should take out your phone and scan this QR code. If I can get it real quick. And that's what I have today. So find me afterwards if you want to learn more about SigStore, how you can get involved. Again, it's an open source project, part of the OpenSSF and Linux Foundation, and we need all the help. So thank you.
Yeah.